Electric power transmission.
Electric power transmission is the bulk transfer of electrical energy, from generating power plants to electrical substations located near demand centers. This is distinct from the local wiring between high-voltage substations and customers, which is typically referred to as electric power distribution. Transmission lines, when interconnected with each other, become transmission networks. The combined transmission and distribution network is known as the power grid in the United States, or just the grid. In the United Kingdom, the network is known as the national grid. A wide-area synchronous grid, also known as an interconnection in North America, directly connects a large number of generators delivering AC power with the same relative phase, to a large number of consumers. For example, there are three major interconnections in North America: the Western Interconnection, the Eastern Interconnection and the Electric Reliability Council of Texas, ERCOT, grid, and one large grid for most of continental Europe. Historically, transmission and distribution lines were owned by the same company, but starting in the 1990s, many countries have liberalized the regulation of the electricity markets in ways that have led to the separation of the electricity transmission business from the distribution business.
System.
Most transmission lines are high-voltage three-phase alternating current, AC, although single-phase AC is sometimes used in railway electrification systems. High-voltage direct current, HVDC, technology is used for greater efficiency at very long distances, typically hundreds of miles, kilometers, or in submarine power cables, typically longer than 30 miles, 50 kilometers. HVDC links are also used to stabilize and control problems in large power distribution networks where sudden new loads or blackouts in one part of a network can otherwise result in synchronization problems and cascading failures. Electricity is transmitted at high voltages, 120 kV or above, to reduce the energy losses in long-distance transmission. Power is usually transmitted through overhead power lines. Underground power transmission has a significantly higher cost and greater operational limitations but is sometimes used in urban areas or sensitive locations. A key limitation of electric power is that, with minor exceptions, electrical energy cannot be stored, and therefore must be generated as needed. A sophisticated control system is required to ensure electric generation very closely matches the demand. If the demand for power exceeds the supply, generation plant and transmission equipment can shut down, which in the worst case may lead to a major regional blackout, such as occurred in the U.S. Northeast blackout of 1965, 1977, 2003, and other regional blackouts in 1996 and 2011. It is to reduce the risk of such failure that electric transmission networks are interconnected into regional, national or continent-wide networks, thereby providing multiple redundant alternative routes for power to flow should such equipment failures occur. Much analysis is done by transmission companies to determine the maximum reliable capacity of each line, ordinarily less than its physical or thermal limit, to ensure spare capacity is available should there be any such failure in another part of the network.
Overhead transmission.
High-voltage overhead conductors are not covered by insulation. The conductor material is nearly always an aluminum alloy, made into several strands and possibly reinforced with steel strands. Copper was sometimes used for overhead transmission, but aluminum is lighter, yields only marginally reduced performance and costs much less. Overhead conductors are a commodity supplied by several companies worldwide. Improved conductor material and shapes are regularly used to allow increased capacity and modernized transmission circuits. Conductor sizes range from 12 mm to, number 6 American wire gauge, to 750 mm to, 1,590,000 circular mils area, with varying resistance and current carrying capacity. Thicker wires would lead to a relatively small increase in capacity due to the skin effect, that causes most of the current to flow close to the surface of the wire. Because of this current limitation, multiple parallel cables, called bundle conductors, are used when higher capacity is needed. Bundle conductors are also used at high voltages to reduce energy loss caused by corona discharge. Today, transmission level voltages are usually considered to be 110 kV and above. Lower voltages such as 66 kV and 33 kV are usually considered subtransmission voltages but are occasionally used on long lines with light loads. Voltages less than 33 kV are usually used for distribution. Voltages above 230 kV are considered extra high voltage and require different designs compared to equipment used at lower voltages. Since overhead transmission wires depend on air for insulation, design of these lines requires minimum clearances to be observed to maintain safety. Adverse weather conditions of high wind and low temperatures can lead to power outages. Wind speeds as low as 23 knots, 43 km per hour, can permit conductors to encroach operating clearances, resulting in a flashover and loss of supply. Oscillatory motion of the physical line can be termed gallop or flutter depending on the frequency and amplitude of oscillation.
Underground transmission.
Electric power can also be transmitted by underground power cables instead of overhead power lines. Underground cables take up less right-of-way than overhead lines, have lower visibility, and are less affected by bad weather. However, costs of insulated cable and excavation are much higher than overhead construction. Faults in buried transmission lines take longer to locate and repair. Underground lines are strictly limited by their thermal capacity, which permits less overload or re-rating than overhead lines. Long underground AC cables have significant capacitance, which may reduce their ability to provide useful power to loads beyond 50 miles. Long underground DC cables have no such issue and can run for thousands of miles.
History.
In the early days of commercial electric power, transmission of electric power at the same voltage as used by lighting and mechanical loads restricted the distance between generating plant and consumers. In 1882, generation was with direct current, DC, which could not easily be increased in voltage for long-distance transmission. Different classes of loads, for example, lighting, fixed motors, and traction railway systems, required different voltages, and so used different generators and circuits. Due to this specialization of lines and because transmission was inefficient for low-voltage high-current circuits, generators needed to be near their loads. It seemed at the time that the industry would develop into what is now known as a distributed generation system with large numbers of small generators located near their loads. In 1886, in Great Barrington, Massachusetts, a 1 kV alternating current, AC, distribution system was installed. That same year, AC power at 2 kV, transmitted 30 km, was installed at Cerchi, Italy. At an AIEE meeting on May 16, 1888, Nikola Tesla delivered a lecture entitled A New System of Alternating Current Motors and Transformers, describing the equipment which allowed efficient generation and use of polyphase alternating currents. The transformer, and Tesla's polyphase and single-phase induction motors, were essential for a combined AC distribution system for both lighting and machinery. Ownership of the rights to the Tesla patents was a key advantage to the Westinghouse Company in offering a complete alternating current power system for both lighting and power. Regarded as one of the most influential electrical innovations, the universal system used transformers to step up voltage from generators to high-voltage transmission lines, and then to step down voltage to local distribution circuits or industrial customers. By a suitable choice of utility frequency, both lighting and motor loads could be served. Rotary converters and later mercury arc valves and other rectifier equipment allowed DC to be provided where needed. Generating stations and loads using different frequencies could be interconnected using rotary converters. By using common generating plants for every type of load, important economies of scale were achieved, lower overall capital investment was required. Load factor on each plant was increased allowing for higher efficiency, a lower cost for the consumer and increased overall use of electric power. By allowing multiple generating plants to be interconnected over a wide area, electricity production cost was reduced. The most efficient available plants could be used to supply the varying loads during the day. Reliability was improved and capital investment cost was reduced, since standby generating capacity could be shared over many more customers and a wider geographic area. Remote and low-cost sources of energy, such as hydroelectric power or mine-mouth coal, could be exploited to lower energy production cost. The first transmission of three-phase alternating current using high voltage took place in 1891 during the International Electricity Exhibition in Frankfurt. A 25 kV transmission line, approximately 175 km long, connected Laufen on the Neckar and Frankfurt. Voltages used for electric power transmission increased throughout the 20th century. By 1914, 55 transmission systems each operating at more than 70 kV were in service. The highest voltage then used was 150 kV. The rapid industrialization in the 20th century made electrical transmission lines and grids a critical infrastructure item in most industrialized nations. Interconnection of local generation plants and small distribution networks was greatly spurred by the requirements of World War I, with large electrical generating plants built by governments to provide power to munitions factories. Later these generating plants were connected to supply civil loads through long-distance transmission.
Bulk power transmission.
Engineers design transmission networks to transport the energy as efficiently as feasible, while at the same time taking into account economic factors, network safety and redundancy. These networks use components such as power lines, cables, circuit breakers, switches and transformers. The transmission network is usually administered on a regional basis by an entity such as a regional transmission organization or transmission system operator. Transmission efficiency is greatly improved by devices that increase the voltage, and thereby proportionately reduce the current, in the line conductors, thus allowing power to be transmitted with acceptable losses. The reduced current flowing through the line reduces the heating losses in the conductors. According to Joule's law, energy losses are directly proportional to the square of the current. Thus, reducing the current by a factor of 2 will lower the energy loss to conductor resistance by a factor of 4 for any given size of conductor. The optimum size of a conductor for a given voltage and current can be estimated by Kelvin's law for conductor size, which states that the size is at its optimum when the annual cost of energy wasted and the resistance is equal to the annual capital charges of providing the conductor. At times of lower interest rates, Kelvin's law indicates that thicker wires are optimal, while when metals are expensive thinner conductors are indicated. However, power lines are designed for long-term usage, so Kelvin's law has to be used in conjunction with long-term estimates of the price of copper and aluminum as well as interest rates for capital. The increase in voltage is achieved in AC circuits by using a step-up transformer. HVDC systems require relatively costly conversion equipment which may be economically justified for particular projects such as submarine cables and longer-distance high-capacity point-to-point transmission. HVDC is necessary for the import and export of energy between grid systems that are not synchronized with each other. A transmission grid is a network of power stations, transmission lines, and substations. Energy is usually transmitted within a grid with three-phase AC. Single-phase AC is used only for distribution to end users since it is not usable for large polyphase induction motors. In the 19th century, two-phase transmission was used but required either 4 wires or 3 wires with unequal currents. Higher-order phase systems require more than 3 wires, but deliver little or no benefit. The price of electric power station capacity is high, and electric demand is variable, so it is often cheaper to import some portion of the needed power than to generate it locally. Because loads are often regionally correlated, hot weather in the southwest portion of the U.S. might cause many people to use air conditioners. Electric power often comes from distant sources. Because of the economic benefits of load sharing between regions, wide-area transmission grids now span countries and even continents. The web of interconnections between power producers and consumers should enable power to flow, even if some links are inoperative. The unvarying, or slowly varying over many hours, portion of the electric demand is known as the base load and is generally served by large facilities, which are more efficient due to economies of scale, with fixed costs for fuel and operation. Such facilities are nuclear, coal-fired or hydroelectric, while other energy sources such as concentrated solar thermal and geothermal power have the potential to provide base load power. Renewable energy sources such as solar photovoltaics, wind, wave, and tidal are, due to their intermittency, not considered as supplying base load, but will still add power to the grid. The remaining or peak power demand is supplied by peaking power plants, which are typically smaller, faster responding, and higher cost sources, such as combined cycle or combustion turbine plants fueled by natural gas. Long-distance transmission of electricity, thousands of kilometers, is cheap and efficient, with costs of $0.005 minus $0.02 per kilowatt-hour, compared to annual averaged large producer costs of 1 cent minus $0.025 per kilowatt-hour, retail rates upwards of 10 cents per kilowatt-hour, and multiples of retail for instantaneous suppliers at unpredicted highest demand moments. Thus distant suppliers can be cheaper than local sources. For example, New York often buys over 1,000 MW of electricity from Canada. Multiple local sources, even if more expensive and infrequently used, can make the transmission grid more fault-tolerant to weather and other disasters that can disconnect distant suppliers. Long-distance transmission allows remote renewable energy resources to be used to displace fossil fuel consumption. Hydro and wind sources cannot be moved closer to populous cities, and solar costs are lowest in remote areas where local power needs are minimal. Connection costs alone can determine whether any particular renewable alternative is economically sensible. Costs can be prohibitive for transmission lines, but various proposals for massive infrastructure investment in high-capacity, very long-distance supergrid transmission networks could be recovered with modest usage fees.
Grid input.
At the power stations, the power is produced at a relatively low voltage between about 2.3 kV and 30 kV, depending on the size of the unit. The generator terminal voltage is then stepped up by the power station transformer to a higher voltage, 115 kV to 765 kV AC, varying by the transmission system and by country, for transmission over long distances.
Losses.
Transmitting electricity at high voltage reduces the fraction of energy lost to resistance, which varies depending on the specific conductors, the current flowing, and the length of the transmission line. For example, a 100-mile 765 kV line carrying 1000 MW of power can have losses of 1.1% to 0.5%. A 345 kV line carrying the same load across the same distance has losses of 4.2%. For a given amount of power, a higher voltage reduces the current and thus the resistive losses in the conductor. For example, raising the voltage by a factor of 10 reduces the current by a corresponding factor of 10 and therefore the I2R losses by a factor of 100, provided the same-sized conductors are used in both cases. Even if the conductor size, cross-sectional area, is reduced tenfold to match the lower current, the I2R losses are still reduced tenfold. Long-distance transmission is typically done with overhead lines at voltages of 115 to 1200 kV. At extremely high voltages, more than 2000 kV exists between conductor and ground. Corona discharge losses are so large that they can offset the lower resistive losses in the line conductors. Measures to reduce corona losses include conductors having larger diameters, often hollow to save weight, or bundles of 2 or more conductors. Transmission and distribution losses in the USA were estimated at 6.6% in 1997 and 6.5% in 2007. By using underground DC transmission, these losses can be cut in half. Underground cables can be larger diameter because they do not have the constraint of lightweight that overhead cables have, being 100 feet in the air. In general, losses are estimated from the discrepancy between power produced, as reported by power plants, and power sold to end customers. The difference between what is produced and what is consumed constitute transmission and distribution losses, assuming no theft of utility occurs. As of 1980, the longest cost-effective distance for direct current transmission was determined to be 7,000 kilometers, 4,300 miles. For alternating current it was 4,000 kilometers, 2,500 miles, though all transmission lines in use today are substantially shorter than this. In any alternating current transmission line, the inductance and capacitance of the conductors can be significant. Currents that flow solely in reaction to these properties of the circuit, which together with a resistance define the impedance, constitute reactive power flow, which transmits no real power to the load. These reactive currents however are very real and cause extra heating losses in the transmission circuit. The ratio of real power, transmitted to the load, to apparent power, sum of real and reactive is the power factor. As reactive current increases, the reactive power increases and the power factor decreases. For transmission systems with low power factor, losses are higher than for systems with high power factor. Utilities add capacitor banks, reactors and other components, such as phase-shifting transformers, static VAR compensators, physical transposition of the phase conductors, and flexible AC transmission systems, FACTS, throughout the system to compensate for the reactive power flow and reduce the losses in power transmission and stabilize system voltages. These measures are collectively called reactive support.
Subtransmission.
Subtransmission is part of an electric power transmission system that runs at relatively lower voltages. It is uneconomical to connect all distribution substations to the high main transmission voltage, because the equipment is larger and more expensive. Typically, only larger substations connect with this high voltage. It is stepped down and sent to smaller substations in towns and neighborhoods. Subtransmission circuits are usually arranged in loops so that a single line failure does not cut off service to a large number of customers for more than a short time. While subtransmission circuits are usually carried on overhead lines, in urban areas buried cable may be used. There is no fixed cutoff between subtransmission and transmission, or subtransmission and distribution. The voltage ranges overlap somewhat. Voltages of 69 kV, 115 kV and 138 kV are often used for subtransmission in North America. As power systems evolved, voltages formerly used for transmission were used for subtransmission, and subtransmission voltages became distribution voltages. Like transmission, subtransmission moves relatively large amounts of power, and like distribution, subtransmission covers an area instead of just point-to-point.
Transmission grid exit.
At the substations, transformers reduce the voltage to a lower level for distribution to commercial and residential users. This distribution is accomplished with a combination of subtransmission, 33 kV to 132 kV, and distribution, 3.3 to 25 kV. Finally, at the point of use, the energy is transformed to low voltage, varying by country and customer requirements. See mains electricity by country.
High voltage direct current.
High voltage direct current, HVDC, is used to transmit large amounts of power over long distances or for interconnections between asynchronous grids. When electrical energy is to be transmitted over very long distances, the power lost in AC transmission becomes appreciable and it is less expensive to use direct current instead of alternating current. For a very long transmission line, these lower losses, and reduced construction cost of a DC line, can offset the additional cost of the required converter stations at each end. HVDC is also used for submarine cables because over about 30 kilometers, 19 miles, lengths AC cannot be supplied. In these cases special high-voltage cables for DC are used. Submarine HVDC systems are often used to connect the electricity grids of islands, for example, between Great Britain and mainland Europe, between Great Britain and Ireland, between Tasmania and the Australian mainland, and between the North and South Islands of New Zealand. Submarine connections up to 600 kilometers, 370 miles, in length are presently in use. HVDC links can be used to control problems in the grid with AC electricity flow. The power transmitted by an AC line increases as the phase angle between source end voltage and destination ends increases, but too large a phase angle will allow the systems at either end of the line to fall out of step. Since the power flow in a DC link is controlled independently of the phases of the AC networks at either end of the link, this phase angle limit does not exist, and a DC link is always able to transfer its full rated power. A DC link therefore stabilizes the AC grid at either end, since power flow and phase angle can then be controlled independently. As an example, to adjust the flow of AC power on a hypothetical line between Seattle and Boston would require adjustment of the relative phase of the two regional electrical grids. This is an everyday occurrence in AC systems, but one that can become disrupted when AC system components fail and place unexpected loads on the remaining working grid system. With an HVDC line instead, such an interconnection would, 1. Convert AC in Seattle into HVDC. 2. Use HVDC for the 3,000 miles of cross-country transmission. Then, 3. Convert the HVDC to locally synchronized AC in Boston, and possibly in other cooperating cities along the transmission route. Such a system could be less prone to failure if parts of it were suddenly shut down. One example of a long DC transmission line is the Pacific DC entity located in the western United States.
Capacity.
The amount of power that can be sent over a transmission line is limited. The origins of the limits vary depending on the length of the line. For a short line, the heating of conductors due to line losses sets a thermal limit. If too much current is drawn, conductors may sag too close to the ground, or conductors and equipment may be damaged by overheating. For intermediate length lines on the order of 100 kilometers, 62 miles, the limit is set by the voltage drop in the line. For longer AC lines, system stability sets the limit to the power that can be transferred. Approximately, the power flowing over an AC line is proportional to the cosine of the phase angle of the voltage and current at the receiving and transmitting ends. Since this angle varies depending on system loading and generation, it is undesirable for the angle to approach 90 degrees. Very approximately, the allowable product of line length and maximum load is proportional to the square of the system voltage. Series capacitors or phase-shifting transformers are used on long lines to improve stability. High-voltage direct current lines are restricted only by thermal and voltage drop limits, since the phase angle is not material to their operation. Up to now, it has been almost impossible to foresee the temperature distribution along the cable route, so that the maximum applicable current load was usually set as a compromise between understanding of operation conditions and risk minimization. The availability of industrial distributed temperature sensing (DTS) systems that measure in real-time temperatures all along the cable is a first step in monitoring the transmission system capacity. This monitoring solution is based on using passive optical fibers as temperature sensors either integrated directly inside a high-voltage cable or mounted externally on the cable insulation. A solution for overhead lines is also available. In this case, the optical fiber is integrated into the core of a phase wire of overhead transmission lines, OPPC. The Integrated Dynamic Cable Rating, DCR, or also called Real-Time Thermal Rating, RTTR, solution enables not only to continuously monitor the temperature of a high-voltage cable circuit in real time, but to safely utilize the existing network capacity to its maximum. Furthermore, it provides the ability to the operator to predict the behavior of the transmission system upon major changes made to its initial operating conditions.
Control.
To ensure safe and predictable operation, the components of the transmission system are controlled with generators, switches, circuit breakers and loads. The voltage, power, frequency, load factor, and reliability capabilities of the transmission system are designed to provide cost-effective performance for the customers.
Load balancing.
The transmission system provides for base load and peak load capability, with safety and fault tolerance margins. The peak load times vary by region largely due to the industry mix. In very hot and very cold climates, home air conditioning and heating loads have an effect on the overall load. They are typically highest in the late afternoon in the hottest part of the year and in mid-mornings and mid-evenings in the coldest part of the year. This makes the power requirements vary by the season and the time of day. Distribution system designs always take the base load and the peak load into consideration. The transmission system usually does not have a large buffering capability to match the loads with the generation. Thus generation has to be kept matched to the load, to prevent overloading failures of the generation equipment. Multiple sources and loads can be connected to the transmission system and they must be controlled to provide orderly transfer of power. In centralized power generation, only local control of generation is necessary, and it involves synchronization of the generation units, to prevent large transients and overload conditions. In distributed power generation, the generators are geographically distributed and the process to bring them online and offline must be carefully controlled. The load control signals can either be sent on separate lines or on the power lines themselves. Voltage and frequency can be used as signaling mechanisms to balance the loads. In voltage signaling, the variation of voltage is used to increase generation. The power added by any system increases as the line voltage decreases. This arrangement is stable in principle. Voltage-based regulation is complex to use in mesh networks, since the individual components and set points would need to be reconfigured every time a new generator is added to the mesh. In frequency signaling, the generating units match the frequency of the power transmission system. In droop speed control, if the frequency decreases, the power is increased. The drop in line frequency is an indication that the increased load is causing the generators to slow down. Wind turbines, vehicle-to-grid and other distributed storage and generation systems can be connected to the power grid, and interact with it to improve system operation.
Failure protection.
Under excess load conditions, the system can be designed to fail gracefully rather than all at once. Brownouts occur when the supply power drops below the demand. Blackouts occur when the supply fails completely. Rolling blackouts, also called load shedding, are intentionally engineered electrical power outages, used to distribute insufficient power when the demand for electricity exceeds the supply.
Communications.
Operators of long transmission lines require reliable communications for control of the power grid and, often, associated generation and distribution facilities. Fault-sensing protective relays at each end of the line must communicate to monitor the flow of power into and out of the protected line section so that faulted conductors or equipment can be quickly de-energized and the balance of the system restored. Protection of the transmission line from short circuits and other faults is usually so critical that common carrier telecommunications are insufficiently reliable, and in remote areas a common carrier may not be available. Communication systems associated with a transmission project may use microwaves, power line communication, optical fibers. Rarely, and for short distances, a utility will use pilot wires strung along the transmission line path. Leased circuits from common carriers are not preferred since availability is not under control of the Electric Power Transmission Organization. Transmission lines can also be used to carry data. This is called power line carrier, or PLC. PLC signals can be easily received with a radio for the long wave range. Optical fibers can be included in the stranded conductors of a transmission line, in the overhead shield wires. These cables are known as optical ground wire, OPGW. Sometimes a stand-alone cable is used, all dielectric self-supporting, ADSS, cable, attached to the transmission line cross arms. Some jurisdictions, such as Minnesota, prohibit energy transmission companies from selling surplus communication bandwidth or acting as a telecommunications common carrier. Where the regulatory structure permits, the utility can sell capacity in extra dark fibers to a common carrier, providing another revenue stream.
Electricity market reform.
Some regulators regard electric transmission to be a natural monopoly, and there are moves in many countries to separately regulate transmission. See electricity market. Spain was the first country to establish a regional transmission organization. In that country, transmission operations and market operations are controlled by separate companies. The transmission system operator is Red Eléctrica de España, REE, and the wholesale electricity market operator is Operador del Mercado Ibérico de Narja, Polo Español, S.A., OMOL. Spain's transmission system is interconnected with those of France, Portugal, and Morocco. In the United States and parts of Canada, electrical transmission companies operate independently of generation and distribution companies.
Cost of electric power transmission.
The cost of high-voltage electricity transmission, as opposed to the costs of electric power distribution, is comparatively low, compared to all other costs arising in a consumer's electricity bill. In the UK, transmission costs are about 0.2p kilowatt-hour compared to a delivered domestic price of around 10p kilowatt-hour. Research evaluates the level of capital expenditure in the electric power T&D equipment market will be worth $128.9 billion in 2011.
Merchant transmission.
Merchant transmission is an arrangement where a third party constructs and operates electric transmission lines through the franchise area of an unrelated utility. Operating merchant transmission projects in the United States include the Cross-Sound Cable from Shoreham, New York to New Haven, Connecticut, Neptune RTS transmission line from Sayreville, New Jersey, to Newbridge, NY, ITC Holdings, Incorporated Transmission System in the Midwest, and PAR 15 in California. Additional projects are in development or have been proposed throughout the United States. There is only one unregulated or market interconnector in Australia, Basalink between Tasmania and Victoria. Two DC links originally implemented as market interconnectors, Direct Link and Moraylink, have been converted to regulated interconnectors. NEMCO. A major barrier to wider adoption of merchant transmission is the difficulty in identifying who benefits from the facility so that the beneficiaries will pay the toll. Also, it is difficult for a merchant transmission line to compete when the alternative transmission lines are subsidized by other utility businesses.
Health concerns.
Some large studies, including a large United States study, have failed to find any link between living near power lines and developing any sickness or diseases such as cancer. One old study from 1997 found that it did not matter how close one was to a power line or a substation, there was no increased risk of cancer or illness. The mainstream scientific evidence suggests that low power, low frequency, electromagnetic radiation associated with household currents and high transmission power lines does not constitute a short or long-term health hazard. Some studies, however, have found statistical correlations between various diseases and living or working near power lines. No adverse health effects have been substantiated for people not living close to power lines. There are established biological effects for acute high-level exposure to magnetic fields well above 100 UT, 1G. In a residential setting, there is limited evidence of carcinogenicity in humans and less than sufficient evidence for carcinogenicity in experimental animals, in particular, childhood leukemia, associated with average exposure to residential power frequency magnetic field above 0.3 UT, 3 mg, to 0.4 UT, 4 mg. These levels exceed average residential power frequency magnetic fields in homes which are about 0.07 UT, 0.7 mg, in Europe and 0.11 UT, 1.1 mg, in North America. Tree growth regulator and herbicide control methods may be used in transmission line right-of-ways which may have health effects.
United States government policy.
Historically, local governments have exercised authority over the grid and have significant disincentives to take action that would benefit states other than their own. Localities with cheap electricity have a disincentive to making interstate commerce in electricity trading easier, since other regions will be able to compete for local energy and drive up rates. Some regulators in Maine, for example, do not wish to address congestion problems because the congestion serves to keep Maine rates low. Further, vocal local constituencies can block or slow permitting by pointing to visual impact, environmental, and perceived health concerns. In the U.S., generation is growing 4 times faster than transmission, but big transmission upgrades require the coordination of multiple states, a multitude of interlocking permits, and cooperation between a significant portion of the 500 companies that own the grid. From a policy perspective, the control of the grid is balkanized, and even former Energy Secretary Bill Richardson refers to it as a third world grid. There have been efforts in the EU and US to confront the problem. The U.S. national security interest in significantly growing transmission capacity drove passage of the 2005 Energy Act, giving the Department of Energy the authority to approve transmission if states refuse to act. However, soon after using its power to designate 2 national interest electric transmission corridors, 14 senators signed a letter stating the DOE was being too aggressive.
Special transmission. Grids for railways.
In some countries where electric locomotives or electric multiple units run on low-frequency AC power, there are separate single-phase traction power networks operated by the railways. Prime example are the countries of Europe, which utilize the older AC technology based on 16 2/3 Hz.
Superconducting cables.
High-temperature superconductors, HTS, promise to revolutionize power distribution by providing lossless transmission of electrical power. The development of superconductors with transition temperatures higher than the boiling point of liquid nitrogen has made the concept of superconducting power lines commercially feasible, at least for high-load applications. It has been estimated that the waste would be halved using this method, since the necessary refrigeration equipment would consume about half the power saved by the elimination of the majority of resistive losses. Some companies such as Consolidated Edison and American Superconductor have already begun commercial production of such systems. In one hypothetical future system called a supergrid, the cost of cooling would be eliminated by coupling the transmission line with a liquid hydrogen pipeline. Superconducting cables are particularly suited to high low-density areas such as the business district of large cities, where purchase of an easement for cables would be very costly.
Single-wire earth return.
Single-wire earth return, SWER, or single-wire ground return is a single-wire transmission line for supplying single-phase electrical power for an electrical grid to remote areas at low cost. It is principally used for rural electrification, but also finds use for larger isolated loads such as water pumps. Single-wire earth return is also used for HVDC over submarine power cables.
Wireless power transmission.
Both Nikola Tesla and Hideshige Yagi attempted to devise systems for large-scale wireless power transmission in the late 1800s and early 1900s, with no commercial success. In November 2009, Laser Motive won the NASA 2009 Power Beaming Challenge by powering a cable climber 1 kilometer vertically using a ground-based laser transmitter. The system produced up to 1 kilowatt of power at the receiver end. In August 2010, NASA contracted with private companies to pursue the design of laser power beaming systems to power low Earth orbit satellites and to launch rockets using laser power beams. Wireless power transmission has been studied for transmission of power from solar power satellites to the Earth. A high-power array of microwave or laser transmitters would beam power to a rectangle. Major engineering and economic challenges face any solar power satellite project.
Security of control systems.
The federal government of the United States admits that the power grid is susceptible to cyber warfare. The United States Department of Homeland Security works with industry to identify vulnerabilities and to help industry enhance the security of control system networks. The federal government is also working to ensure that security is built in as the U.S. develops the next generation of smart grid networks.
Records.
Highest capacity system, 6.3 GW HVDC at Itaipu, Brazil Paraguay, ± 600 kV DC. Highest transmission voltage, AC. Planned, 1.20 MV, ultra high voltage, on Wada-Aurangabad line, India, under construction. Initially will operate at 400 kV, worldwide, 1.15 MV, ultra high voltage, on Ekaterinburg line, Kazakhstan, Europe, under construction, 750 kV, extra high voltage, on the Rivne NPP Khmelnytskyi NPP to Kyivska substation route, Ukraine, planned, 1.20 MV, ultra high voltage, on Wada-Aurangabad line, India, under construction. Initially will operate at 400 kV, worldwide, 1.15 MV, ultra high voltage, on Ekaterinburg line, Kazakhstan, Europe, under construction, 750 kV, extra high voltage, on the Rivne NPP Khmelnytskyi NPP to Kyivska substation route, Ukraine, largest double-circuit transmission, Kita-Iwaki power line, Japan, highest towers, Yangtze River crossing, China, height, 345 m or 1,132 feet, longest power line, Ingushuba, Democratic Republic of Congo, length, 1,700 km or 1,056 miles, longest span of power line, 5,376 m, 17,638 feet, at Amralikspan, Greenland, Denmark, longest submarine cables. Norned, North Sea, Norway Netherlands, length of submarine cable, 580 km or 360 miles, Baselink, Bass Strait, Australia, length of submarine cable, 290 km or 180 miles, total length, 370.1 km or 230 miles, Baltic cable, Baltic Sea, Germany Sweden, length of submarine cable, 238 km or 148 miles, HVDC length, 250 km or 155 miles, total length, 262 km or 163 miles. Norned, North Sea, Norway Netherlands, length of submarine cable, 580 km or 360 miles. Baselink, Bass Strait, Australia, length of submarine cable, 290 km or 180 miles, total length, 370.1 km or 230 miles. Baltic cable, Baltic Sea, Germany Sweden, length of submarine cable, 238 km or 148 miles, HVDC length, 250 km or 155 miles, total length, 262 km or 163 miles, longest underground cables. Maralink, Riverland Sunraysia, Australia, length of underground cable, 180 km or 112 miles. Maralink, Riverland Sunraysia, Australia, length of underground cable, 180 km or 112 miles.